We left off discussing that the linear regression model will try to figure out what are the best values for beta naught and beta 1 to draw the line through our data set. But we didn't talk about what exactly is it doing. Is it doing some sort of trial and error? Is it guessing? Or how is it going about choosing what are good values of beta naught and beta 1 to reduce the mean squared error? Well, one way the algorithm can do to figure out what's the best value of beta naught and beta 1 is applying gradient descent. So for this plot here, let's go ahead and plot the result, the mean squared error, for various values of beta 1, various values of the slope. So we're going to set the beta naught, the intercept, constant, and we're just simply going to play around with modifying beta 1, modifying the slope of the line. So you can think if we go back here, what we're doing is let's measure the error if we start pivoting these lines for different angles, for different slopes. And note, we kept beta naught constant, but we could have also modified it. If we had modified it, we would have generated a two-dimensional space as opposed to a one-dimensional space. So we have the error metric on the y-axis, the value of the slope on the x-axis. And we see here that the lowest value occurs right about there. Looks about anywhere from, let's say, greater than 1400 and less than 1430. So we look at the true answer, it says 1410. So this matches up what we saw before. Anything that's interesting about the following curve? Well, if we look at this curve, we have a minimum value. That's one thing we need to know. Notice its shape, right? It's a convex shape. So let's apply gradient descent. So what gradient descent is going to do is it's going to start off at some initial point in our search space. Let's say, for example, we're going to start off at a very bad point in space. We're going to start off up right here in this corner of the graph. It's a very high error. Let's see how this algorithm is going to go about moving such that I can find this minimum value here. The way the gradient descent works is that it's going to calculate the gradient at some starting point. Then using that gradient is going to decide which direction it should step. And the reason why it's going to use the gradient is because the gradient will tell you the local direction of greatest ascent. In other words, if you find the gradient at a certain point, that tells you the direction you must go to increase the function's value. Since we want to decrease this function value, we're going to take the opposite step. Think about it this way. Let's say you are hiking in some space and you're trying to find the valley. And let's say it's very foggy. So you can't see where you're going. You can only see locally, maybe a few feet from where you're positioned. And you notice that a certain direction will take you down the farthest at that point. So you're going to take a step in that direction. Take a step in that direction, you can see a little more of your surroundings, and then you decide, given where you are now, where should you next step? That's basically what gradient descent is doing. You start off with a point, you figure out the direction of greatest descent, and you take a step in that direction, and you reevaluate. Where should I step next? And you repeat the process. It's an iterative scheme. It's an iteration. You repeat it until you've reached this minimum value. So here, at this point, there's only two options. Should you go further to the left or further to the right? Should you decrease beta 1 or should you increase beta 1? Given the direction, it's telling you, what? You should move towards higher values of beta. And that's what it'll do. The model will take a step towards higher values of beta and reevaluate. Okay, here I am in space. Where should I move next? Oh, it still says that I should keep on moving to the right. Because I keep on moving to the right, I will decrease the cost function. I'm further reducing the cost function. Remember, this cost function is what I'm trying to reduce, try to minimize, and by modifying my model parameters, modifying my model coefficients. We repeat the process and you can see what's going to happen eventually. Eventually, it's going to reach this minimum value. It's going to stay there because at this point, if the algorithm moves any further to the right, it'll notice it's going to increase the error. It's going to increase the cost function. So it knows no longer to move in that direction. It has found the global minimum. This is the point. This is the beta 1 value that's going to reduce the cost function by the most. So that's what the parameter it's going to decide to use for the analysis. Now I want to say when working with linear regression, you might be wondering, well, are you guaranteed, is this algorithm guaranteed to converge to the true value or the lowest value of the cost function? When we are dealing with linear regression, we are guaranteed to converge to the global minimum of our cost function. So long as we take small enough steps in our gradient descent search. You can imagine if we're taking very large steps, we can go ahead and miss this valley here. Think of it if you are a giant and you are hiking, you're trying to find the lowest point, your steps are very large, you can possibly bounce around and not find the minimum value. But for linear regression, we have a convex problem, so we have given this shape. You should find the minimum value if the step size is small enough. I wouldn't worry about playing around with the parameters. Some of these hyperparameters that are going on involving finding this particular minimum value. When you're using linear regression, you can modify some of those things, but the default values are best to use. Just letting you know what's going on underneath the hood. Other models are going to use gradient descent, very similar approach, to figure out the minimum value of the cost function. What are the best model parameters to minimize the cost function? Now this was all based upon minimizing the mean squared error. There is a different model called the Huber regressor. What the Huber regressor does, it's a linear model. It says that the labels are linearly related to the features. There's a linear relationship, just like we have drawn out here. Except the difference between the Huber regressor is the cost function the model is going to use. So instead of minimizing the mean squared error, figuring out what is the beta coefficient to reduce the mean squared error, instead it's going to minimize a different cost function. Let me draw out this cost function. So let me throw this question at you. What is a problem with using a mean squared error? What are some problems we might run into with using this cost function? This model is susceptible to outliers because of that square term. We don't have a linear penalty, we have a square term in calculating the error metric. So our model will really suffer if there are outliers present. And we understand we can use a cost function that it uses the absolute value instead. But you remember what was the problem with the absolute value? What was a concern about using a cost function that has an absolute value? It's not differentiable along this vertex here. But we can go ahead and modify our cost function. This is going to be a problem because if we're going to use something like gradient descent to figure out the beta coefficients, figure out the model coefficients, then it's going to be a problem if certain parts of our space we can't take the derivative. So instead, what we're going to do is, if the problem point is around 0, we can go ahead and use, try my best job here, a quadratic error term. This is a quadratic error term here, in a small region around the 0 point here. But outside this region, we will use a line. I know that's my best job at drawing a line. So I have a line there. So this right here is a line. but the space here is quadratic. And now this cost function is differentiable across the entire space. So this is called the Huber-Loss cost function. So if we use the Huber-Loss model, it's not using the mean squared error, but it's using this modified approach. So it's going to handle better outliers. All right, you can believe me that's going to better handle outliers, but let's go ahead and prove it. Let's actually show an example. So if we go back here, if we let's look at some outliers or some points that really deviate from our model. And if we do some visual inspection, things like this point there really deviate from our line. So there's a big penalty for this point there, especially consider the black line. And those outliers are going to influence the slope for our model because there's a large penalty. It will push the slope, push the line, push that line closer to that outlier point at the cost of better fitting other points in our data set. So it has a greater influence because of that square penalty. So let's use a Huber-Loss. So we're going to import the Huber-Loss, create it. We're going to fit it with that one variable we've been looking at. So right now we just have a single variable. X1, we'll expand it later. Let's go ahead and use the model to plot the results. We'll plot with the linear regression model. So linear regression is a sort of standard linear regression with the square loss is in black, and the Huber-Loss is in purple. So notice what you see from this figure. What do you see from this figure? What is happening here? Now, since the Huber-Loss uses a linear loss for most of its space, these outliers are no longer going to have a great influence to the shape of our model, the shape of the line, the slope of our line. So that's why it's not so much pushed towards those higher values. It's pushed downward. You can think of these points here, or just since they deviate a lot, you can think of as gravity. They're pushing the slope to better accommodate it, to better fit it, because it has a very large error because it's squared. You can see the differences between the Huber-Loss and the simple linear regression model.